number 2, frequency domain analysis. We will talk about the frequency measurement and also the combination of signal with different frequency. First, we will measure the frequency of the sine wave signal. The frequency is set at 1 kHz with peak to peak amplitude 2 volt. And press FFD to see the frequency domain. And you can use the scale knob to adjust the sampling rate of the oscilloscope. And make sure the sampling rate is more than twice the frequency of the signal. And use the cursor pattern to measure the frequency and also the amplitude and frequency domain. And you need to select the FFD, and the type is either frequency or magnitude depending on what you want. This is the theoretical calculation of the sinusoidal signal, sine wave, in frequency domain. So you need to find a V root mean square voltage and then transform it into dB root mean square using this formulation. It is supposed to be minus 3 dB Vrms for the amplitude of 1 volt. So here you can see we have approximately minus 3 dB here. However, this formulation is not applicable for the square wave and the triangular wave. You need to follow the Fourier series for theoretical values. So let's see the experimental result. So here you will see a lot of harmonic, and the first frequency and then second, and the triangular signal also the same. So you can compare with the Fourier series formulation. So now we will change the voltage into 4 VBP, peak to peak, and then theoretically we should get 3 dB Vrms. The second part is the aliasing. Aliasing means we use the round sampling rate. So when it happens, the actual frequency will be considered as a lower frequency or the higher frequency, giving you the round result. So our signal frequency is 5 MHz. This is the formula to get the sampling time. So with frequency 5 MHz, sampling time should be less than 0.1 microsecond. In this experiment, we can see that when the sampling time base is not less than 0.1, we can see the aliasing. So the correct sine waveform is not appearing here. So experimentally, there is no aliasing when the time base is less than 1 microsecond. In frequency domain, it is simple. So 2 times the maximum frequency, so which is 10 MHz. So here you can see this one is sample per second, which means sampling frequency. Here you can measure the frequency using the cursor. At 2.5 megasample, we cannot see any frequency. And when we increase into 50 MHz, you can see the correct sample frequency, which is 5 MHz. The last part is combination of different signal and also filtering, separating the signal. Here we use another open amplifier to invert the negative output to the positive one. So here we will first combine the 1 kHz and 8 kHz signal. Both has 10 VBP. So here I'm showing the original signal, one of the original signal, and then the combined signal. The blue one is the 1 kHz frequency signal, The yellow one is the combination signal, and you can see the graph is not correct because I didn't turn on the power supply. So to get the frequency of the resulting signal, you need to find the fundamental frequency, which is to find the GCD, the greatest common divisor. So here I select the source channel 1, which is the combination of the signal, and make sure your sampling rate is higher than the maximum frequency. So here you can see both frequency in frequency domain. So this is, you can see both 1 kHz and 8 kHz. So here I'm trying to find the frequency of both signal by using the magnitude cursor. Now I'm going to show the separation of the signal using RC circuit. So in order to pass the low frequency, we'll give the input from the resistor and the output across the capacitor. And for the high pass filter to pass the high frequency, the input will be given to the capacitor and the output will be measured across the resistor. And then make sure that the positive side of the oscilloscope rod will be given to the joint node of the capacitor and the resistor. So here this is the high pass filter, which pass the high frequency 8 kHz. The yellow one is the high frequency, only high frequency is passed, which is 8 kHz. And when we measure across the capacitor, you will have the low pass filter, and which is you can see it's 1 kHz and it has higher magnitude dB than the 8 kHz. Even though it is not a perfect filter, we can still see 1 kHz frequency. So if you use the second order or other different filter, you will have a better result. So thank you for watching. I will see you guys in the next